This section explains why propositional logic is the first move in the book. 2 arguments, the late train forcing taxis at the station and the rain forcing Jane's umbrella, from examples 1.1 and 1.2 turn out to be the same argument. Written as a skeleton, it reads, if P and not Q, then R, not R, P, therefore Q. That coincidence is the whole chapter. Strip away what the sentences mean, and only their connective skeleton remains. Validity lives entirely in that skeleton, never in the content. So, the chapter's job in the book's arc is to forge the first symbolic language where the word therefore stops being intuition and becomes a mechanical, truth-preserving calculus over declarative atoms. Atoms here are sentences that can, in principle, be true or false, and nothing finer. The generative move is this. An argument is valid when no substitution of atoms makes the premises true, and the conclusion false. This part explains what the chapter means by a valid argument, and why validity is something a machine can check. Strip a valid argument of its content. The trains, the rain, the umbrellas, and what survives is pure shape. If P and not Q, then R. Not R, P. Therefore, Q. Examples 1.1 and 1.2 are the same argument wearing different words. That erasure is the chapter's whole premise. That erasure is the chapter's whole premise. Validity is a property of form, so a machine can check it. The chapter then makes the notion of follows from precise and finds that it splits in 2. There is a syntactic notion where you build a proof by pushing rules, written with the turnstile, P proves Q. And there is a semantic notion where truth survives every valuation, written with the double turnstile, P entails Q. The generative payload is that these 2, defined independently, turn out to coincide exactly. That coincidence is soundness and completeness. Proof and truth are the same boundary drawn twice. This section explains what predicate logic gains over propositional logic. A propositional atom is opaque. The sentence, every student is younger than some instructor, collapses to a single letter P, and every inference that turns on its interior, the quantity, the relation, is lost. Predicate. Logic's move is to make the atom transparent. It decomposes the sentence into individuals, into predicates that ascribe properties and relations to them, written S of X or Y of X and Y, and into quantifiers for all, and there exists binding variable placeholders. So the formula, for all X, if S of X, then there exists a UF of X. If S of X, then NSE my such that I of Y and Y of X and Y now carries the logical structure that propositional atoms discarded. The generative primitive is this. Expressive power comes from quantifying over the interior that a coarser logic left sealed. Everything the chapter builds after this, proof theory, semantics, is the price of reasoning inside that open structure. This section explains what Chapter 2 does to a proposition. A propositional atom is opaque. One symbol, P, swallows the sentence every student is younger than some instructor and forgets everything inside it. Chapter 2's whole move is to crack the atom. A sentence stops being a black box truth bearer and becomes a predicate applied to terms. You write S of X or Y of X and Y with quantifiers, the universal for all and the existential there exists, binding variables that range over an implicit domain of individuals. Resolution rises. The sentence's internal dependence, an instructor per student, becomes sentence's internal dependence, an instructor per student, becomes expressible Everything after this is Chapter 1's three-angle program, proof theory, syntax, and semantics rerun at this finer grain. The primitive to keep is this. Quantification is exactly what you gain the moment you refuse to treat a proposition as atomic and expose the objects it silently ranges over. This section explains how verification splits into two families, and the split turns on where the search lives. In the proof-based family, the system is a set of axioms called gamma, and the specification is a formula called phi. You hunt for a derivation of phi from gamma, a proof, and you hunt for it across a possibly infinite class of models. This search is expert-guided and manual. The model-based family collapses that search. You fix one finite model, called M, and you merely compute whether M satisfies phi. Satisfaction against a single object replaces entailment over a whole class, and finiteness makes the check decidable, hence automatic. Model checking is this second corner, sharpened for reactive, concurrent systems. Here, truth turns dynamic. The formula phi holds at some states and fails at others. M is a transition system, and phi is temporal. So verification becomes evaluation over a graph. When that evaluation fails, it returns the falsifying execution trace. The counterexample is the payload. This part explains why verification splits into two moves, proving or evaluating, and why evaluating is the cheaper one. Verification splits into two moves, prove or evaluate, and the chapter's thesis is that evaluating is cheaper. Proof-based checking asks whether phi follows from a system description, gamma across every model, an infinite search needing human guidance. Model checking replaces that with a single object. You build one transition system, M, and you compute whether M satisfies phi. Deduction collapses to evaluation. It becomes decidable, automatic, for finite M. The shift that enables this is temporal logic. Truth stops being static and becomes state, indexed, so a formula's value evolves as the system runs. Failure returns not a bare no, but a counterexample, trace, the execution that breaks phi. The whole method is one model, one property, one decision procedure. This section explains why program verification abandons model checking and proves correctness by induction on code structure instead. Model checking dies where data lives. Admit a single integer variable and the state space becomes infinite, so exhaustive enumeration collapses. The move is to replace checking with proving. Chapter 3 walked every state. Here you construct a proof by structural induction on the program itself, exactly as predicate. Logic's proof calculus escaped enumerating infinitely many models of a sequent. The unit is the Hoare triple, written as a precondition phi, then the program P, then a postcondition psi. Start P in any state, satisfying the precondition phi, and if it terminates the result, satisfies the postcondition psi. A program becomes an implication between two assertions, and verification composes over the four constructs: assignment, sequencing, if, and while. It never composes over runs. The primitive is this. Correctness is proved by induction on code structure, not enumerated over an unbounded state space. This part explains why infinite state forces a shift from model checking to theorem proving. Infinite state kills enumeration. The moment a program holds an integer variable, running P halts in a state where psi holds. Where psi holds in a state where psi holds can no longer terminate. So you stop checking runs and start proving one theorem, the Hoare triple, written as a precondition phi, then the program P, then a postcondition psi. It reads, if the precondition phi holds, running p halts in a state where psi holds. The generative move is the same escape, Chapter 2, made from checking infinitely many models. You induct on the program's syntax rather than its runs. One proof rule per construct, composed up the parse tree. Assignment, sequencing, and branching fall out mechanically. Only the while loop demands invention and invariant. The human spark, no algorithm supplies. Verification becomes structural induction over code rather than simulation of it. This section explains modal logic as a single relation on worlds and how that relation turns into a theory of agents. The move the whole chapter turns on is that truth stops being absolute and becomes indexed to a world. You replace the single valuation of propositional logic with a set of worlds and a relation saying which world can see which. Two operators ride on that relation. The box operator means true in every visible world. The diamond operator means true in some visible world. The relation is the tunable knob. Make it reflexive, make it transitive, make it symmetric, and each property corresponds to an axiom, so the family K, T, S4, and S5 is just one relation dialed through its shapes. The payoff is agents. Read visible as epistemically indistinguishable, and the box operator becomes knows. A modal system is then a theory of a knower. One relation on worlds generates the entire zoo. You predict a system by naming its relation. This section explains why truth becomes many. Valued the moment it arrives in modes, and how modal logic captures every mode with a single move. Truth stops being a single bit the moment you let it arrive in modes: necessary, known, future, believed. Modal logic buys all of them with one move. You quantify a proposition over the world you can reach. Box phi holds when phi is true in every accessible world. Diamond phi holds when phi is true in at least one. These are the universal and existential quantifiers for all, and there exists, stripped of their variables. The generative primitive is that the mode lives entirely in the accessibility relation. Read, reach as physical possibility, and box becomes necessity. Read it as an agent's ignorance, and box becomes knowledge. Read it as time, and you recover the Kripke models of CTL. Huth and Ryan take a logic engineering stance. Name a mode, build its logic. That whole program reduces to one act. You choose the relation R. This section explains binary decision diagrams and why their reduced form makes equivalence cheap. Fix an ordering of the variables, then read a Boolean function as a decision tree, but never store the same subfunction twice, and never branch on a variable that changes nothing. Those two reductions, sharing identical subgraphs and skipping inert tests, quotient the exponential tree into a reduced ordered BDD. The surprise is that this normal form is canonical. Under one ordering, a Boolean function has exactly one such graph. So equivalence, the expensive question everywhere else in the book, degrades to checking whether two pointers name the same node. Satisfiability is the question. Is it the terminal 0? A tautology is the terminal one. The chapter's payload is this. Represent a function by its canonical collapse, and semantic questions become structural identity. This section explains why the shape you choose to write down a Boolean function is a bet, and which representation wins that bet. Every representation of a Boolean function is a wager on which operation stays cheap. Truth tables make satisfiability a glance. Is there a 1 in the last column? But they pay 2 to the n in space. Propositional formulas compress beautifully, yet they bury satisfiability under SAT, whose cost is suspected exponential. The chapter's move is to engineer a representation that is canonical, one function, exactly one object. Then equivalence collapses to pointer identity and satisfiability collapses to a walk down a graph. That object is the reduced ordered binary decision diagram, the efficient Boolean substrate beneath the model checking of Chapter 3. The primitive to carry is this. Choose the normal form whose defining structure is the question you needed answered.